Okay, so on this video, we're going to take a look at the idea of composites, composite functions. First, we'll go ahead and look at it from a table view. Here is an input into a function called f of x. So here are the domain values, or the inputs, and for example, when you put 1 in for x, f of 1 is negative 1. And here's a second function, and here are the x values, and when you put one of these in, you get an output to the g function that goes across this row. But what we're going to do is f of g of a value. In other words, we're going to do a composite function. And this notation really means that we are first taking the g function on a value, on an input or domain value, and then taking that result as the corresponding input into the f function. So what I have here is really something that maybe can be described generally like this. The composite f of g of x is really finding the output to the g function and using that for the input to the f function. So let me just give you an example with f of g of 5, and then we'll just look. This happens to be a multiple choice question. We'll see if we could find the answer down here once we solve it for ourselves. So I'm going to first, if I'm looking specifically at f of g of 5, I'm going to evaluate the g function for an input of 5. And if I do that, if 5 goes into the g function, the output, g of 5, is 11. So right now, I have f, and now what I'm going to do is, since the output for putting 5 into the g function is 11, that is going to go into my f function as an input. And I'm doing a composite of functions. I'm doing a function on a function. And so now I use 11 for the input. That was the output to the g function. And I'm using it as the input to the f function. So I go up here back to the f function and I put 11 in. And when I put 11 into the f function, f of 11 is 2. And the final answer to this composite of f of g of 5 turns out to be 2. And it looks like our answer is B. Okay, well, let's take a look at doing this ourselves, where we actually generate the composite function. I mean, we already had the inputs and outputs of the function here without having to deal with a specific function ourselves. But this time, let's take a look at a problem like this. So once again, we're looking at a composite, f of g of x. We're going to look at it in a general way. We're not going to put a specific x value in there. But we're going to create the composite function. And what we're going to do is say that if the f function is to multiply x by 8 and add 15, and the g function is to multiply x by 5 and subtract 1, what would the composite function be of f of g of x? Well, in a similar way to what I did up above, where I said f of g of x is really the f function on the g of x function as an input. Let's put this g of x function of 5x minus 1 into our f function as an input. But we're going to do it in a general way this time. We're not going to deal with a specific value. So I'm going to really say that when I am finding f of g of x, what I'm really doing is I am going to put the g of x function in as an input to the f of x function, and it's going to look like this. My input to the f function is the g of x function. And so I'm going to get this. When I evaluate this f of x function, it's to multiply by 8, whatever the input is. But my input is actually a function. It's g of x, which is 5x minus 1. So I'm going to do this. Instead of 8 times x, I'll have 8 times 5x minus 1. I'm literally putting the g of x function in for x plus 15. I simplify this, and I would have 40x minus 8 plus 15 is 40x plus 7. And that is my f of g. I could write it either way. I like this notation personally. It seems to give me a better feel for the fact that I'm putting the g of x function into the f function to find f of g of x as a composite function. Now, it looks like, back to this multiple choice option here, I'm looking at this D for the answer. I think that is the answer to this, right? The answer is this right here. Okay. Now, finally, let's take a look at a function where I'm going to go ahead and do a composite function, but on some kind of an application. So what I got here is a situation where I'm going to go ahead and first look at the function which has to do with the surface area of a balloon, and that is a geometric formula of, if you know the radius, the surface area, like just the skin of the balloon, how much area is, if you could go ahead with it still being inflated, cut it apart and lay it out flat, how much area would that cover? That is found by 4 pi r squared. The only thing is, it says the radius of this balloon, like as if it was hooked up to a pump where it is consistently increasing the volume of it. And by the way, this is assuming a spherical kind of balloon, right, shaped like a sphere. As this blows up, its radius is changing with time at the rate of, it's a rate function, it's a radius as a function of time function, that our radius is growing at the rate of 2/3 t cubed, with t being time. So every time you increase the time, you would you would raise that time to the third power and multiply by 2/3, and that would give you the corresponding radius at that particular time. Well, what we want to do is see if we could come up with a single function, rather than having to put a certain time in here, get a radius, and then put that radius into the surface area function. Could we get a composite function that would directly take us from time and immediately get a surface area? That is a composite function. So what I'm going to do is this. I'm going to say that I am really after S of t. I'd like to find surface area as a function of time by doing the following composite. Maybe what I could do is take my original surface area as a function of radius and put, instead of radius, a specific radius of, like, say 5 inches or whatever, let me put my radius function in there. So now radius will be represented generally as a function of time. So I'm going to get to my surface area as a function of time function by doing this, putting the radius as a function of time function in once and for all, in for radius, in my function here, my S of r function. So what that would look like is this. It'd be, instead of r, I'm going to go ahead and use my r of t function right there, and I will get this. My function, let me go ahead and actually just do the work. It's going to be 4 pi, and instead of radius, I'm going to put the radius in terms of time function in there, and it's going to be putting 2/3 t cubed in for the radius, and I'm still squaring. So I'm really using the S of r function, but I'm putting r of t function in for r. So once and for all, I'll have a relationship now between surface area and time, and here it is. Now I could go ahead and simplify this a little bit. Let me show you. It's just a little bit of arithmetic. Think about it. I am raising this quantity to the second power. It's really like saying this. 2/3 t cubed times 2/3 t cubed. Well, that's going to give me 4 pi times 2/3 times 2/3 is 4/9. And t to the third times t to the third, you add powers when you multiply bases, will be t to the 6th power. And so now what I have is really, I can multiply here. These are all factors, but I can multiply here, and I will have 16/9 pi t to the 6th power is my S of t function. right here. Right? And I'm not sure if that was on the screen, so let me go over that again. I can multiply here by 4 times 4, and I get 16, 9 on the bottom, pi t to the 6th. Now, by the way, I mean, let's say that somebody asked me then to directly find the surface area of a balloon after 2 minutes, assuming that this is growing at this rate and time is in minutes. Okay, I don't know if it tells me in here. I'm looking. I don't think it gave me a specific value. But if this is time in minutes, then what would happen here is I would go ahead and put a 2 in there, and I'd evaluate this. If what is the surface area of the balloon at 2 minutes, then it would be 16 over 9. That's just a page number, by the way, so I'm going to get rid of that. And this would be times pi times 2 raised to the 6th power. And I would get my calculator out, and let me just go ahead and do that. And I could put this all in. I think I'll use my fraction feature right here. And so I'll go alpha y equals, and I'll put the 16, put the 9 in the bottom. I right arrow to escape the fraction. I'm going to hit second pi, second, and then this symbol here, which would give me pi if I had second and then that button. And then what else do I need? I need times 2 to the 6th power times 2 raised to the 6th power. And this gives me a surface area of 357.44 square inches, right? It's in square inches, equals 357.44 square inches, right? And that would be at a time of 2 minutes. And you see what I avoided there, because I now have this composite function, is I did not have to come up with the radius. Did you notice I didn't really know the radius of this? I indirectly knew it, because the radius was built into the time. The radius, as a function of time, was embedded into my surface area function. Otherwise, I would have had to separately work through 2 minutes in my radius function and then put that radius in. I would have gotten the same answer, but now I have a composite function doing that directly.